Bone is a highly dynamic, living connective tissue, a metabolic structure that constantly remodels its own internal architecture. This living tissue handles three distinct physiological roles, providing rigid skeletal support, shielding vital internal organs, and facilitating physical movement. The primary engineering challenge lies in how one biological material accomplishes all three tasks simultaneously. The skeletal system manages these competing demands through a strict morphological taxonomy, classifying bones by their shape and internal structure. This classification divides bones into 6 foundational categories: long, short, flat, irregular, pneumatic, and sesamoid. These 6 categories represent specialized engineering solutions to specific biomechanical loads. Long bones are defined strictly by their dimensions. They are physically longer than they are broad. The central cylindrical structure providing this length is the shaft, anatomically known as the diaphysis. Capping this central cylinder are 2 articular extremities, known as the epiphyses. Inside the diaphysis sits a weight-saving feature, the medullary cavity. This hollow core keeps the bone light without compromising its structural integrity. This architecture is utilized in the limbs, including the femur, the humerus, the tibia, and the radius and ulna of the forearm. By combining a rigid shaft with articulating ends, these bones operate as levers for movement and as architectural columns that support body weight. Short bones follow a different macroscopic geometry. As the definition notes, they are strictly cuboidal in shape. Internally, they feature a shock-absorbing core of cancellous bone, tightly wrapped in an outer layer of dense compact bone. Found in the carpal and tarsal bones of the wrist and ankle, they provide localized strength and stability for areas requiring highly limited movement. Long bones sacrifice localized stability for dynamic leverage. Short bones do the inverse, sacrificing leverage to serve as high-strength junctions. Flat bones are thin, typically curved structures. They utilize a sandwich architecture, featuring 2 dense outer layers of compact bone. These dense layers encapsulate a porous middle layer of cancellous bone, known as the diploe. In the skull, sternum, ribs, and scapula, this structure provides high-impact resistance to shield vital organs, while broad surfaces offer area for complex muscle attachments. Irregular bones are categorized by exclusion. These possess shapes too complex and non-uniform to fit into standard geometric categories. The vertebrae, the hip bone, and cranial structures like the sphenoid and temporal bones all fall into this group. Flat and irregular bones prioritize spatial accommodation and organ defense, proving that when the skeleton requires complex shielding, it discards standard leverage geometry. Pneumatic bones are defined by their internal air-filled cavities. These cavities are known as sinuses and are lined by mucous membranes. Located in the skull, like the frontal bone and maxilla, these cavities reduce cranium mass and serve as resonance chambers for the voice. Sesamoid bones are defined by their biological location. They are small, rounded bones embedded entirely within tendons. The patella is a primary example. Sitting inside the tendon, it acts as a biological pulley, modifying muscle pull direction and reducing mechanical friction. Pneumatic and sesamoid bones operate as evolutionary hacks, solving engineering problems like cranium weight and joint friction that standard bone morphology cannot resolve. Macroscopic shape explains what a bone does, but structural characteristics alone don't fully classify human osteology. This leads to the secondary classification system, osteology according to embryological development. Membranous bones ossify directly within a membranous sheet. This direct formation is responsible for the flat bones of the skull. Cartilaginous bones develop by slowly replacing a pre-existing cartilage model, which is how long bones are formed. Morphological shape is the physical manifestation of a strict embryological blueprint, linking developmental origin to final mechanical capacity. When observed in its entirety, the complex human skeleton functions as a fully assembled biological engine in motion. The system is an aggregation of specialized mechanical parts, each engineered for a distinct purpose. Long bones provide leverage, short bones provide stability, flat bones act as shields, while irregular bones manage complex junctions. Pneumatics reduce weight, and sesamoids act as pulleys. This primary morphological shape is rooted in its secondary classification, its embryological development. In human osteology, macroscopic geometry guarantees physiological capability. Form and function are locked together within the bone.